So ignore your handout for a second. Let's look at, let's do 3 squared equals 9. So that's an exponential form. What would it look like in logarithm form? Log base 3 of 9 equals 2. So logarithms solve for the exponent instead of what we called the answer before. Okay? Well, what if I did 3 to the 5th? What is 3 to the 5th? You're going to need your calculator, so pull it out. 243. Yeah, right. Okay, well, is there a 3 squared inside the 3 to the 5th? What I mean is, so could I find this problem inside that problem? So if I wrote 3 squared, what would I times that by? 3 to the 3rd, which is the same as 9 times 27. Okay? Is 9 times 27 243? You guys know what you're doing. All right? So if I converted this into logarithms, it would be log base 3 of 243 equals 5. Could I split the logarithm in the same way that I splitted the exponential equation? So I want to represent this as a logarithm, which is a little more difficult. So instead of trying to convert it, let's look at the logarithm and make the changes. So it's still going to be log base 3. What do I split the 243 into? 9 times 27 equals 2 plus 3. Whoa, that's really weird. So we took the 243 and we changed it into 9 times 27. Agreed? And then we took the 5, which used to be a second exponent and a third exponent. Well, those exponents are added together, so it turned into 2 plus 3. Okay? Well, that's really strange. What is log base 3 of 9? 2. What is log base 3 of 27? 3. So what you're saying is, if I take log base 3 of 9 and add it to log base 3 of 27, that's the same thing as log base 3 of 9 times 27. This is one of the rules of logarithms. Okay? And you see it here. So let me write it out a different way. Log base 3 of 9 plus log base 3 of 27 is exactly the same thing as log base 3 of 9 times 27, which is the same thing as log base 3 of 243. Sorry, that arrow's in the way. Do you guys see that? This is called the product rule of logarithms. If you have the logarithm of two numbers multiplied together, you can actually split them into two separate logs that are added together. The reason being, right here we have a 2 plus 3. If the bases match, what do you do to the exponents? You add them. So right here, we have two logarithms. Log base 3 of 9, which has the exponent of 2, and log base 3 of 27, which has the exponent of 3. So if the bases are the same, which they are, you can add the logs together. Or, yeah, you can add the two logarithms together. Okay? And we'll spend more time on the product rule later. But that brings up a really interesting point. If I had log base 3 of x to the 4th power, that's the same thing as log base 3 of x times x times x times x. Right? So I can split that 4 ways. Log base 3 of x plus log base 3 of x plus log base 3 of x plus log base 3 of x. Does that make sense? Well, if I have 4 versions of the same thing added together, that's really just 4 times the log base 3 of x. And that's the great secret with logarithms. If I skip all this middle stuff, I get log base 3 of x to the 4th equals 4 times log base 3 of x. You take the exponent and turn it into a multiplication problem, and that is the magic of logarithms. This will solve all of our problems. Well, at least all those guessing problems we had before. So if you have, and the base doesn't matter, so I have some log, and then I have a number with an exponent on it. That exponent can be removed and placed in front of the log as a multiplication problem. Remember the trouble we had where we had x's in the exponents? This will allow us to pull those x's down and turn it into a multiplication problem. And we can stop guessing. So this is called the power rule. This rule here, from this step to this step, is called the product rule. There's also a quotient rule, where you use division and subtraction instead of multiplication and addition, but that's for tomorrow. Right now we're going to focus on the power rule. So if you look at the top of your worksheet, so it gives the power rule. If you have log base a of x to the y, you're allowed to grab that y and stick it in front of the log. So let's look at when the rule applies and when the rule does not apply. So number 1, can we apply the rule? Yes, and the answer would be 2 times log base 5 of 7. Okay? What about in part 2? Well, x times y is just a number, right? So it could be the number z. So log base 6 of z raised to the p. Can we pull that exponent down? Yes. So p times log base 6 of xy. What about number 3? No, why not? You're squaring. So this is the base. This is the answer. And together, it's an exponent. A logarithm represents an exponent. And it's an exponent to the second, which the power rule does not apply. So whatever you want to write, I don't care. Number 3 does not work. Okay. Number 4, you can pull down the CD, because C times D is just one number inside those parentheses. So CD times log base A of B. And number 5, I'm getting yeses and nos. Hannah, why not? What is the exponent on the 2? It's 2 to the first times x to the second. So we have an exponent of 1 and an exponent of 2. Which one do we use? Neither. The only time you can do it is if they're both 2's. So if you look back at number 2, number 2 is actually x to the p, y to the p. And because they share the same exponent, you can pull that p out. But on number 5, you're looking at 2 separate exponents, and you can't take either. You can't even take the average. If you pulled down a 1.5, it wouldn't work. So number 5 is not possible. Okay. So we have log base 3 of 9, which translates into 3 to the x equals 9. What number makes that true? 2. So x equals 2. If we slide this over, we have 3 to the x equals 26. So that first question asks, what's wrong with the second problem? It's not a whole number. We'll get there in a second. Okay? So, what would we expect the answer to be? It's between 2 and 3, obviously. And it's going to be really, really close to 3. Right? So 3 squared is 9. 3 to the third is 27. So 26 is probably 2.9, something like that. So this question asks, what would you expect the answer to the second problem to be? It's probably 2.8 or 2.9. Well, you know what would be really nice? Is if we could ask the calculator, what is the log base 3 of 26? So I want to know log base 3 of 26. But the calculator does not have a log base 3 button. And it will never have a log base 3 button. That would just make your life too easy. Your calculator does have 2 log buttons. Let me teach them to you. So if you look on your calculator, on the left side, you see an LOG button. That means log base 10. Whenever you have a logarithm without a written base, it's always 10. Okay? So, if I wanted to know log base 10 of 100, what is that in your head? 10 squared is 100. So if I type in log of 100, I should get the number 2. Okay? What about log base 10 of 1,000? So log of 1,000 is 3. What if I changed it to log base 10 of 4,000? It's going to be between 3 and 4. Is it closer to 3 or closer to 4? Probably, well, let's try it. So log base 10 of 4,000, and I get 3.6, which is kind of confusing because 4,000 is not as close to 10,000 as it is at 1,000, but it's exponential, so. Okay, that's nice. What if I want log base 5? Stay tuned. Nope. Now, every logarithm is different. So you guys understand that the square root is not the same as the third root, which is not the same as the x root. Every root acts different. Well, your calculator has an x root button, so you can plug in any number you want. There is no log base x button. Am I dragging this out long enough? Okay, but we don't need one. Another really common log is log base e. And you guys probably, have you ever seen the letter E, the number E? I doubt it. It's E equals 2.71, and it's an irrational number just like pi, and E shows up in calculus all over the place. It's the exponential number. That's where E comes from. So log base e is actually called the natural log. So abbreviated, it would be ln. Is anybody a Spanish student? How do you say greenhouse in Spanish? Casa verde, right? House green. So in all Latin languages, French, Spanish, Italian, Portuguese, what did I forget? Anyways, all the Latin languages, it's always noun, adjective. Well, back in Europe, we had all of these really smart people. They lived in England and France, um, Spain, Italy, Portugal, all of these countries that spoke Latin languages. So instead of everybody learning everybody else's language, everybody learned Latin. When you went to school, you spoke Latin. That way, you could change countries and you could still go to school. All of the textbooks were written in Latin. So when this mathematics was developed and written in the textbooks in Latin, it was something like Logarithmus Naturalis, which is abbreviated ln, and then in England, people did things backwards, and natural log is kind of backwards, but we abbreviate it ln. So ln is actually log base e. So that's nice. They gave us two buttons. They gave us base 10, and they gave us base e. What about all the other bases? Stay tuned. You know the answer? Oh, you did? Oh, that's annoying. It doesn't exist. It's just a figment of your imagination. So she found a log-based button, but trust me, it's not worth your time. Because there's a way faster way to do it. You cheated! Okay. So go back to your worksheet. And let's consider this log base 3 of 26 equals x. Well, we don't know what to do with the log version, so let's go back to the exponential version. 3 to the x equals 26. Well, we learned about the power rule, and we also know that if we make changes on one side of an equal sign, it's perfectly fine as long as we make the same changes on the other side. So let's take the log of both sides. And every log has to have a base, and I don't know which base to use, so I'm just going to pick the letter b. So I'm going to take log base b of both sides. Now it's still true, it's still equal, and does the power rule apply to this problem? Yeah, I can pull down the x. So if I grab this x and pull it down, I now have x log base b of 3 equals log base b of 26. Can I solve for x? Well, what's holding the x and the log together? Multiplication, so I just divide. And x is log base b of 26 divided by log base b of 3. Now, at what point did I use the number b? How much effect did b have on the problem? Nothing at all, right? So if it was a 6, is that any different from a 10? No. As long as it's the same on the top and the bottom. So the original problem was log base 3 of 26. So this is claiming I can take any logarithm I want, and I can change it into a different base by taking the 26 and putting it on top, and the 3 and putting it on bottom, and I can pick my own base. So I could use base 10, which is on the calculator, or I could use base e. So if I did the log of 26, close the parentheses, divided by the log of 3, Is that what I expected? Yes, I was expecting 2.9. Let's try it with the natural log. The ln of 26 divided by the ln of 3. Same answer. What if I did the log over the natural log? So the log of 26 divided by the ln of 3, that does not work. So the change of base formula says if you have a logarithm, you can change it into any base you want as long as you use the same base on the top and the bottom. So Tristan made a liar out of me. She went and found a log base button. You don't know how to use it yet, though. You figured it out? Oh. So you could use that, but then you'd have to look it up every time. You might as well just do the log of the number divided by the log of the base. And just for simplicity's sake, I always use the natural log for two reasons. One, it's one fewer letter to write down on your assignment. And two, sometimes the natural log makes things easier depending on the particular problem. So you could use log or natural log, but you'll see me use natural log almost all the time. And it doesn't really matter. Now, you guys might think this is tough, but before calculators, here's how you used to look up logarithms. So you had log base 3 of 26. Okay, so you open your logarithm textbook, you go to chapter 3, which is base 3, and you flip through the pages until you find log base 3 of 26 and you look up the number. So the really nasty logs were kind of terrible. Log base 3.1 of 15.875. So you'd have to look up chapter 3.1, and then you'd have to go down the charts until you found 15.875, and then it would have the decimal equivalent written out to the side. They really had these textbooks. My last year in college, I saw one. It was a book like this big, and all it had was logarithm calculations. Now, if you were smart, you didn't need every chapter. You could do the change of base formula to find them, but then you'd end up dividing decimals, which is a mess. So we don't do that. So let's use our new knowledge to answer number 6. So log base 5 of 72. I don't have a log base 5 button. So all I need to do is log of 72. Wait, is that what it was? Yeah, 72 divided by the log of 5. Oops. Whatever. 2.65. Pretty simple, right? So now, when you answer each of these, if there's a fraction, make sure you put the fraction in parentheses, whether it's a base or whether it's the number you're taking the logarithm of. Fractions have to be in parentheses. So this worksheet should be a breeze. I mean, you should be able to figure out all the answers the easy way. I do want you, when we take the test, I want you to write down what you type into your calculator. So Chaseley's doing it the right way. So Chaseley is writing down log base, and it's not actually b. You could either do log of 72 over the log of 5, or ln 72 over the ln of 5. So you do need to pick a b, but you only have two choices. It's either 10 or it's e. And in both cases, we don't actually write the base. If it says log, then the base is a 10. If it says ln, then the base is an e. So you can just delete these b's. Okay. All right. Simple enough. Tomorrow we'll learn more about the product and the quotient rules. Tomorrow means Thursday.